Alright, so this is on section 10.2, which is on transformation of initial value problems. So in this section, you're going to learn how to use the Laplace transforms to solve differential equations with initial conditions. But before that, we're going to do a theorem first. So this is the central theorem of this section. So suppose our function f of t is of exponential order as t goes to infinity. So let's recall what this means from section 10.1. This means the absolute value of f of t is bounded by a constant times e to the ct as t grows larger and larger. If this holds, then the Laplace transform of f prime exists. Not only does it exist, we have a formula for it, so it's equal to s times the Laplace transform of f minus f of 0, which can be written as s times capital F of s minus f of 0. This holds for s greater than c here. So this is not hard to prove, so let's actually prove it here. So by definition, the Laplace transform of f prime is equal to the integral from 0 to infinity of e to the negative st times f prime of t dt. And here we're going to use integration by parts. So this is our u, and this is our dv. So integration by parts tells you this is equal to u times v evaluated at 0 infinity minus the integral of du, which is negative s e to the negative st dt times v. So let's simplify it. This is equal to negative e to the negative st times f of t from 0 to infinity plus s times integral of the rest of terms. So here are a few things to notice. This thing, by definition, is equal to the Laplace transform of f of t for s is greater than c. And second, because of the condition f of t is of exponential order, so this converges for s is greater than c. So we only have the term at 0 left. So when we plug in t equal to 0, we get negative f of 0, and then the second term is s times the Laplace transform of f of t. So this is equal to s times the Laplace transform of f of t minus f of 0, which is what we had in the statement. We can also rewrite this as s times f of s minus f of 0. Now this can be generalized to higher derivatives. So let me rewrite the conclusion we just had. The Laplace transform of f prime of t is equal to the s times the Laplace transform of f of t minus f of 0. So if we want to do the Laplace transform of the second derivative of t, of f, then we know that the second derivative is equal to the derivative of the first derivative. So we can rewrite it this way with different colors. But we can use the conclusion we just had, that this is equal to s times the Laplace transform of f prime of t minus f prime of 0. And now we can apply this statement again to the new term. So this is equal to s times parentheses s times the Laplace transform of f of t minus f of 0 minus f prime of 0. So if we simplify it, what we get is s squared times the Laplace transform of f of t minus s times f of 0 minus f prime of 0, which is equal to s squared times f of s minus s times f of 0 minus f prime of 0. So that's the Laplace transform for the second derivative. And this can be generalized to higher derivatives. So for example, the Laplace transform of the third derivative of f is equal to s cubed times cap f of s minus s squared times f of 0 minus s times f prime of 0 minus f double prime of 0. And then this generalized to all the higher derivatives. But we're going to mostly use the second derivative in this class.